For our next section, we're going to be learning how to find the volume of solids. Now, what I decided to do in honors calculus is actually divide this section into two parts. And so for part A, we're going to be focusing on how to find the volume of an irregular solid. Now, an irregular solid would be a shape that's not geometric. It's not just a cylinder or a sphere, because of course if it was, we could just use geometry formulas. So what if it's an irregular solid? How would you find the volume? And to strengthen that, how would you use integrals to find the volume? Well, to answer that, I'd like you to take a look at this sample irregular solid that I created out of Play-Doh.
Okay, so the first thing to notice is that it's a solid. It's a three-dimensional object, and it's irregular. It's not any kind of normal geometry shape. Now, I made it out of Play-Doh. I have to admit that I miss being able to do this with you guys in the classroom. You actually would have gotten a lump of Play-Doh and you guys would have been able to make some of these shapes. But if we want to find the volume of this, it turns out that what we're actually going to do is we're going to cut it into cross sections. Now, if you cut this into cross sections, you notice something. And, well, I want you to notice that you get a, now we're going to call this two-dimensional. You have to kind of pretend that I cut this paper thin. You get a two-dimensional object, and its shape would be that of a circle. And so it turns out that if you actually would visualize cutting this entire object into cross sections, you would end up with an infinite amount of cross sections. And these infinite amount of cross sections, of course, would be an infinite amount of circles that eventually we would be able to stack together. We'd be able to add them together. And when you add together an infinite amount of two-dimensional objects, you end up with a three-dimensional shape. That is, you would end up with the volume of this shape. Let me show you how to do it on paper.
So we partition or slice the object into cross sections. And what we say is that each cross section has a cross-sectional area. In other words, it has a two-dimensional area. But if you take a cross-sectional area and you multiply it by a thickness, we're going to call this the change in x. Now, students will often say, what do you mean delta x or the change in x? That would be like an infinitely thin dimension. But nonetheless, I have two dimensions, that is area, and I'm going to multiply it by a third dimension, that is the change in x or the thickness. That's going to end up giving me a volume. Now, here's the neat thing. A cross-sectional area will be able to be thought of as a formula. It'll be some type of area formula. And the change in x, delta x, will be able to be thought of as dx. Now remember, this statement right here represents the volume of each one of those cross sections. So all we need to do now is add them all together. We need to add an infinite amount of them together. And how do we add, or how do we accumulate different values? We do an integral. So if you do the integral of a of x dx, what you're really doing is you're adding together all of those little volumes to become a total volume of the irregular solid. And this simple formula is going to end up being how we will always find the volume of an irregular solid. Again, it'll be the integral of the area times dx. Now you guys are going to learn that the area, or the cross-sectional area, becomes the main component in these problems. That is, trying to determine what would be the cross-sectional area for a given shape. Now I'm going to encourage you to look at that guided notes paper that I included with this lesson, because the wording behind these shapes is sometimes can sound a little confusing. I'm going to help you guys to interpret the wording as an object, and we will end up being able to decipher then the cross-section for that. Now the first one we're going to do is a three-dimensional object. It's got a flat bottom, and it's basically between the square root of x and negative the square root of x from 0 to 9. Now here's the key statement. The cross-sections, this is what you want to pay attention to, are squares whose bases are going to fit in the xy plane between these curves, also perpendicular to the x-axis. What is this object going to look like?
Okay, so we have to make a shape that has a flat bottom that fits between these square root curves, but also has square cross sections. Now, if you take a close look at this, you can kind of see that the object, it's three-dimensional, but if I slice it, I should be able to see a square. I should be able to see a square as the cross section. And we're gonna pretend that this was pretty close to a square. But the truth is that every slice in this object would have made a square. And I pre-made a version of this that is entirely cross sections. And I want you to see how each slice gets bigger, but yet each one of them is a square. And so what we're gonna do is we're gonna need to figure out the formula for the area of one of these squares.
So to come up with the area of one of these cross sections, it might be helpful to draw. Now, my three-dimensional drawing is not too good, but what I'm trying to do here is draw a square that would be sticking up off the paper. Of course, it could also be a square over here. In fact, all of these cross sections are going to be squares. Now, our main objective is going to be to find the area of one of these squares. So what we want to do is we want to start by making a statement that would be true, and that is that the area of any square is always the side squared. But we're going to want now to adapt this formula to fit this actual situation, that is a square that's between these square roots. Now, I want you to start to focus in on the side itself. We'll put it in purple now because our goal is really to come up with how long that side is. Now, you don't want to tell me that it's 3 or 4 or 5 units long, but rather you want to understand that it's going to be a expression. It's going to be some type of formula for S. So now the question is, how long is that? Now, to answer that, a student needs to understand that this distance right here, in other words, half of the side, would be equivalent to the square root graph, because the graph itself is a y value, and again, that distance would be represented by that single y value, by the square root of x. It would also be true that this distance, this other half, would also be a length of the square root of x. Now, sometimes students will say, well, why is it not negative? You have to understand that we're talking about dimensions here, so we want like an absolute value. So the question is, how long is this entire side? And that would have to be 2 square roots of x. Now, 2 root x is the length of the side, and that's what I'm going to be able to substitute into my little formula. But we can see now that our formula starts to kind of simplify. In other words, I can express it as 4x. And the key here is to understand that we now have a formula for the area of a cross-section, and that formula is represented by 4x. That's the hard part. The easy part is coming up with the volume. You see, the volume is always going to be the integral of the area formula times dx. That's right, it's always that simple. It's going to be the integral of the area formula times dx. Because what you're really doing is you're adding together an infinite amount of these square cross-sections. And each of these square cross-sections, when the area is added together, will become a volume. And of course, that is that three-dimensional size that we seek. Now, there's many ways that you can integrate this. We've done this a number of times. Keep in mind that you can do it by hand. I'm sure I'm going to ask you to do one of these by hand, where you find the antiderivative by adding to the exponent. You can then plug in f of b and f of a. Ultimately, what you're doing here is squaring 9. That comes out to be 81, and twice that is 162. You could also use f and I and t. You'll have that option, but keep in mind that this is now a cubic size, a cubic dimension that is the volume of that three-dimensional object. Now, this example was for square bases. You're going to find out that we're actually going to do 4 problems, each of them representing a different cross-section. So whenever you have a cross-section that's a square, then obviously you're going to be focusing on the formula side squared. But what if you have a cross-section that is a circular disc? In the case of this problem, it's the same surface, it's the same region between the square roots of x, but now our cross section is going to be described with circular discs whose diameters are between the curves and perpendicular to the x-axis. Now again, what does this object look like? What does it look like to have circular discs that have diameters that are between these curves? Now the diameter would be this distance, but what does the object look like, and what are the cross sections going to be?
All right, so what does this three-dimensional object look like? Well, it's got to have some more roundness to it. Now, the shape that I've made here, actually there's a reason that it's not quite right, although it seems like it's got a cross section that's a circle, and it's between the XY plane. There's a problem with the diameter. Now, the problem with the diameter is that the diameters are not running between the square roots. It turns out that we actually want to have half of the object above the plane and half of the object below the plane, because now your diameters of these circles are going to be running between the square roots. And that's exactly what we want. We want to be able to slice down on this and end up with a circle whose diameters run between the square root curves. So what would the formula be for the area of that cross section?
So to find the area of one of these cross sections, it might be helpful to try to draw in one of these circles. Now, this is hard to do because it's actually supposed to be coming up off the paper. In fact, half of it's above the paper and half's below. But it gives us an idea to think about a circle. And, of course, the diameter is running the whole way between the square root curves. So the area of a circle, well, we want to start with that being, of course, pi r squared. And that allows us to very quickly realize what we need to do is we need to describe the radius. Now, again, the radius is not going to be a number. It's not going to be 3, 4, 5, but rather it's going to be an expression. So the question becomes ultimately, how long is that purple length? How long is that radius? And from our previous discussion, we know that that is the same as the equation. The square root equation, that is its y value, is representing that distance, so we can say that the radius is equal to the square root of x. Now, when you plug that radius into the formula for the area of a circle, there's a little bit of simplifying that can be done. In fact, obviously the square and the square root cancel, leaving us with only pi x. Now, here's what you want to understand. Pi x is the area of a cross section. That's where we want to be. We want to find the area of a cross section because the volume's easy to do. The volume is just the integral of the area of a cross section times dx. And of course, when you do the integral of the area, it's like you're adding together an infinite amount of circles. And when you add together an infinite amount of circles from 0 to 9, you create that three-dimensional object that I showed you. In other words, you create its volume. All right, so f and I and t, antiderivative, but your answer comes out to be 127. So if we have a cross section that is a circle, we're going to be thinking about the radius. We're going to be thinking about pi r squared and getting a radius that matches. So are you ready for our next three-dimensional irregular solid? This time what we're going to do is we're going to look at an object that is between the equation 2 sine of x and the x-axis. But here's the main part. Its cross sections are now semicircles whose diameters are going to fit between this plane and these curves perpendicular to the x-axis. So what's this object going to look like?
So what's this three-dimensional object going to look like? Well, it's kind of interesting because it has a flat bottom, but it also has a rounded top because the cross sections are semicircles. So it's got to fit between the sine wave, as you can see here. It's a little bit rounded on the top, but here's the main thing. When I slice it, I'm going to end up with a cross section that's a semicircle. Now, technically, every slice would create a semicircle because I would have an infinite amount of these slices stacking together an infinite amount of these semicircles. I want you to take a look at a version of this that shows all these cross sections. I want you to see how each one of the cross sections, it's a semicircle, but it's a different size. So our goal is going to be to describe the area of each one of these semicircles using the sine wave.
All right, so do you feel like you're starting to catch on to these irregular solid problems? This will be the part of the lesson where students start to feel like they can do this a little more on their own. Remember, we're thinking about cross sections. It might be helpful to try to draw one. It's not easy to do, but we kind of have this idea that there's a semicircle that's coming up off the paper. Of course, what we want to do is we really want to find the area of that cross section. So we have to ask ourselves, what's the area of a semicircle? I hope that you would say it's a half of pi r squared, which leads us to the main thing here, which is to come up with an expression for r. Okay, now again, don't tell me that r, just kind of real quickly, is the sine wave, although you're catching on if you know that it has something to do with the sine wave. Because what you really want to realize is that the radius would actually be only this distance. So, how long is that? How long is that distance? Okay, this whole distance, that would be the sine wave, 2 sine. But what about only half of the distance? That's right, it would only be half of your 2 sine wave. Now we want to be careful here because half of our 2 sine wave is actually going to simplify to be just sine. And so we end up with an expression, or really a formula, that says that the area is 1/2 of sine squared. Okay, now, once again, that's the main thinking. In other words, that's the area of the cross section. The easy part is finding the volume. I feel like you can set it up. Okay, you should be integrating. I should be mentioning that these limits of integration are definitely the x values that are part of our sketch. And just to make sure that we're seeing this correctly, they would definitely be represented by the boundaries of this region. So this blue dot is pi, the first blue dot was 0, so we got that going on. But our main thing here is to integrate the area function times dx. Okay, we want to integrate the area function times dx. Just a point here to mention, this 1/2 is part of the area formula. Sometimes students will confuse that with the 1/2 that was used in the discussion of the radius. They are 2 separate 1/2s. Again, the green 1/2 was because it was a semicircle. The purple 1/2 is because we only wanted half of that full distance. So make sure that each one has its place. But it's time to integrate. Just a side note here, you actually would not be able to do the antiderivative of this problem without f and I and t. That's because we don't know how to do the antiderivative of sine squared. We can't make it a substitution problem because we don't have something that's going to cancel. So it's interesting. You can't do the problem without a calculator. I do encourage you to type this into f and I and t. If you have not typed one of these into f and I and t yet, make this the first one. And make sure that you can get 2, 4, 6, 7 units cubed. So f and I and t of 1/2 pi sine squared from 0 to pi will give you that volume. So this was for semicircles. Notice that semicircles used a 1/2 of pi r squared. So now we have one more cross section to show you, a cross section that will involve equilateral triangles. So look at how this is worded. We have cross sections that are equilateral triangles whose bases now will run between the x-axis and the curve. So one last time, what's this object going to look like? And what will be the area of one of its cross sections?
All right, well, I hope you haven't let me have all the fun with these Play-Doh shapes, but if you have, I'm still going to show you this last one. It's my favorite shape because it's got these straight sides, and of course those straight sides are the sides of a triangle. Now, notice that the shape is inside the graph again, the region, but here's the key. If you slice it, and this is what this lesson's all about, is thinking about these cross sections. If you slice it, you end up with an equilateral triangle. And of course, each one of these cross sections
is actually going to be a different sized equilateral triangle. If you look at my version here, you can see that each of these triangles gets a little bigger as we move along the curve, but our goal is going to be to find the area of one of these triangles. Now the equilateral triangle cross section is probably the trickiest of all of them, just because the formula for the area of a triangle is a little bit more involved. But maybe we should first draw one of these equilateral triangles. That kind of helps us then to think about the formula that we're working with. Now, 1/2 base times height, that's not tricky. But what's a little tricky is actually coming up with the base and height for this actual triangle. Now, what I'm going to do is I'm going to take this triangle that I drew over on the sketch, and we're going to kind of pull it over here and make it more upright so that we can start to get it labeled. Like the base. The base would be this entire distance here, which definitely is the graph. It is the 2 sine of x. That's pretty easy to determine, and so we have our base. What's a little tricky to determine here is the height. Now, we don't want to make a silly statement like the height is also 2 sine of x. But it is true that the height has something to do with the 2 sine of x. Because you see, the height is part of a right triangle, and that right triangle shares an equilateral side. That is, its hypotenuse would be equivalent to that 2 sine of x. And with a little bit more digging, we would be able to describe this half side that is part of our right triangle. And that's the key. It is half of the full 2 sine of x. And of course, half of that is going to just be sine of x. Now, what we've done here is we've been able to describe a leg and hypotenuse of a right triangle so that we can now describe the other leg. And that other leg is going to be our height. So kind of off to the side here, we're going to say that side squared, that is leg squared, plus the height squared, that is the other leg squared, is going to equal our hypotenuse squared. Now, the part that students usually, or at least could have trouble with in this problem, is realizing that we have to square the entire hypotenuse. So that means we're squaring the 2 and the sine of x. So we get ourselves a algebra equation that we're basically solving for h, and knowing that 2 sine squared is actually 4 sine squared, we can subtract this blue sine squared over here and end up with a height that's going to equal 3 sine squareds. Now, I'm sorry, the height squared is equal to 3 sine squareds, which means that if I solve that by taking the square root of both sides, now I have a height that's actually equal to the square root of 3, the sine of x. Of course, the squares can cancel on the sine. So, do we have enough information to be able to write an area formula? Well, I believe we do. We're going to take our base and we're going to fill that in. That was determined to be 2 sine of x at the beginning of the problem. And now we're going to take our newly found height and we're going to fill that in. That's been determined to be root 3, the sine of x. And as we've done with the other problems, if there's some simplifying that can be done, simplify away, because you want to come up with the simplest area formula you can find. Yes, the half and the 2 cancel, and yes, the sines are able to multiply to be a sine squared, and so when everything settles out, we have an area formula of 1/3 sine squared of x. Now, that's the hard part. The easy part is, but make sure you do this, is that you do the integral of your area. And remember, when you're doing the integral of the area, that's because you're actually adding up all of those cross sections. And when you add up an infinite amount of cross sections, you end up getting volume, because what was 2-dimensional gets added together to be 3-dimensional. And just like the other problem that we did, you actually cannot do the antiderivative without f and int. So make sure you know how to do f and int. Typing something like this with the square roots and the square, it actually will give you the number 2721. And of course, that's our volume. So if we have equilateral cross sections, we're going to be thinking about 1/2 base times height, and honestly thinking mainly about the height by doing a little bit of that Pythagorean theorem. All right, now it's your turn. I have carefully created an exit ticket that's going to try to force you to do the thinking that's required to get the ball rolling with these irregular solids. Now, I'm going to help you think about this one a little bit. Normally in class, you'd have to think about this just with your neighbors. But just take a look. We've got a square cross-section. Okay, since we have a square cross-section, you could, before you do anything else, you would have 100% certainty that your formula is going to be a side squared. And what we really want to do is we want to come up with a expression for the side. Now, this is where students sometimes have some trouble. Let me help you think about the side. You see, it says that the squares are going to be fitting between these curves. They're going to be fitting in between here. So the question really becomes, how long are these green lines? Now, don't tell me that they're 4 or 3. They change, they vary. So how long are these green lines? Well, they are the distance between the two equations. So how do you find the distance between two equations? Well, I'm going to help you here, and the answer is you subtract. You see, a distance is always going to be the subtraction or the difference between your two equations. So in this case, it would be the upper equation or the upper graph minus the lower equation or the lower graph. And if you subtract your two equations, you're going to get the distance between them. Now, remember, the distance between your two equations is actually going to be your side length. So you're going to have to carefully take whatever you find here and then plug it into your area formula. That area formula is what ultimately should be simplified and put here so that you then can turn it into an integral and then, of course, end up with that final volume. Okay, now there's 2 questions. I helped you get started on the first one. You're going to want to submit these questions to me using the upload form so that I can give you some feedback before you start working on your assignment. One comment about your assignment, there are some really good 3-dimensional drawings. Please use those 3-dimensional drawings to help you think about the cross sections.